All right, so let me start with a question for you. If you could design the perfect machine, what would be its most essential feature?
That's a good one.
Because for most of human history, we've always prioritized things like speed or strength or
Processing power, that sort of thing.
Exactly. But what if the ultimate feature was just the ability to survive, to take a huge hit, suffer some catastrophic damage, and then just fix itself automatically?
Well, that idea, that dream of giving a machine biological resilience, that was pure science fiction for decades, right? If a robot broke, a human had to fix it, period.
Or you just had to scrap it.
Exactly. But today, we're doing a deep dive into a breakthrough from MIT that just completely flips that whole paradigm on its head.
That's right. We are talking about a true self-healing soft robot. A flexible machine that can recover from cuts, punctures, you name it, entirely on its own.
And often within minutes with no human intervention at all.
This isn't just some new flexible material. It really feels like a blueprint for the next generation of truly autonomous systems.
So our mission today is to give you the full picture. We're going to unpack the material science, what they call dynamic covalent polymers, which is really the secret sauce.
Okay.
Then we'll look at why the focus on soft robotics is so critical for this to work and what it all means for everything from future space missions to maybe even the safety of things in your own home.
Let's start right there with the fundamentals. When we say soft robot, we need to be clear this is different from other flexible robots we've seen. Those are still, pretty fragile.
Right.
So what did MIT actually build, and why is the soft part of it so important here?
The material is everything. Your traditional factory robot is rigid, all metal, built for precision, for brute force.
Yeah.
Soft robots they're the opposite. They're built from materials that are meant to mimic biological tissue. So they're flexible, they're malleable, sometimes almost jelly-like.
And the MIT innovation basically embeds that resilience, that toughness, directly into the material structure.
Exactly. So it's not just designed to be soft, to, say, absorb an impact. The material itself is actively fighting back against damage.
So if it gets cut, it doesn't just sit there. It automatically reconnects and seals the wound. No glue, no tools.
No human repair needed. It stitches itself back together right at the molecular level.
How does it do that?
It's all thanks to something called self-repairing polymers. Now, these kinds of smart plastics have been in development for a while, but the real achievement here was getting them into a working robotic structure.
Into an actuator, you mean?
Right, into an actuator, and optimizing them for a fast structural repair. The robot isn't just plugging a leak, it's actually restoring its own structural integrity.
And that difference is huge, isn't it? Restoring integrity versus just patching a hole. If you think about it, the biggest problem for robotics has always been some minor damage leading to total failure.
Oh, absolutely. A tiny crack in a joint, a puncture from some debris, that's usually mission over, or at least a very expensive downtime.